The dog is? Even names are like freaks and yeah. They can also it's all yeah.
Okay. So we're happy to welcome Valery Kiryukhin from Rutgers University. Valery got his PhD from Princeton University, working with Bernard Keimer, and then postdoc with Bob Birchenow at MIT. And then he's been at Rutgers for some time now, using neutron and X-ray scattering techniques to look at all kinds of interesting magnetic materials. I guess in those materials, there's been kind of a problem that the most interesting types of magnets, antiferromagnets, have these larger scale domain structures, but it's really hard to actually see those domain structures. In many cases, we didn't know how to measure them. And recently, Valery kind of invented a technique that allows us to actually look at movies of these things, which is pretty amazing. He's going to hopefully tell us about that today. So thanks.
Thank you for inviting me here. I had some wonderful conversations today. Very interesting. So yes, I'll be talking about imaging antiferromagnetic domains and catching them in action. This is work obviously is done in collaboration with my research group at Rutgers, as well as with the sample growers, Cheong's group at Rutgers and J.J. Young at NJIT. And, a lot of people come from the X-ray scattering facilities, Brookhaven National Laboratory in this case. So this is outline. I'll talk about ferromagnets and antiferromagnets and try to convince you that magnetic domains are important. Turns out that antiferromagnetic domains are difficult to image, and there are some techniques for doing this, but those techniques are necessarily limited. We introduced new technique for imaging antiferromagnetic domains, which is applicable to many antiferromagnetic types, including the so-called antiphase domains. I will explain what I mean by that. The technique produces direct images and works in real time, which is very important. So, using that, I will show you the first movies of fluctuating antiferromagnetic domains in real time and space. If time allows, I'll talk about zebrafish. So, of course, what else? Magnetic materials. This is what one thinks about when someone mentions magnetic materials, right? And we have a lot of applications of magnetic materials in information storage, power generation, electric vehicles. I have little kids. This is what is important for me. All right. So ferromagnets are what comes in mind, right? And in a ferromagnet, you have atoms. Each atom possesses a magnetic moment, and these moments are aligned in the same direction. So you have the north pole, the south pole, right? And an important part in the physics of ferromagnets is that you can switch their magnetization, right? If you apply a magnetic field in a certain direction, the magnetization changes from up to down. And in the process, the magnet typically doesn't switch smoothly. The switching occurs through the formation of the so-called magnetic domains, which are distinguished by the direction of the north and south, right? Now, ferromagnetic domains have ubiquitous and numerous applications. This is the one I'm sure you know about in the information storage. This is the one your dad knows about, and I remember very well, right? I can tell you what it is, but that saying is good, all right? It records music, and it records it on a magnetic tape where you have ferromagnetic domains distinguished by different directions. Now, there are numerous imaging techniques of ferromagnetic domains because they produce magnetic field, and after all, this is the imaging device actually for ferromagnetic domains, just the output is especially pleasant, all right? Ferromagnets come in one variety, basically. This is a ferromagnet, right? Now, you can also have the magnetic moments in matter arranged differently in such a way that that the total magnetization adds up to zero. You know, this is what comes in mind once again. This is the proverbial antiferromagnet, but unlike in a ferromagnet, there are numerous ways to arrange magnetic moments in space to produce zero magnetization. These are all antiferromagnets, right? You can arrange them in 3 dimensions like this. You can have spin density waves. You can have helical arrangements of spins. You can have a lot of other things, right? So there are many different varieties of antiferromagnets. And until recently, the applications of antiferromagnetic domains were, well, basically none, right? Now, it is being realized that antiferromagnetic domains could be very much important for practical applications, specifically in the field which is called antiferromagnetic spintronics. And there are several fundamental reasons for this. Firstly, you can switch them faster. They produce small stray fields, and therefore they are immune to noise. And, as I said, there is a large variety of antiferromagnets leading to various ideas of their application. Now, what I'm showing here is kind of long and complicated, but the main message here is that one can switch antiferromagnetic domains by application of an electric current. And this is a non-trivial statement because switching ferromagnetic domains is easy. You just apply a magnetic field to them and they switch. The question is, if you want to have a functional application of an antiferromagnetic domain, you need to have some way of switching it, right? An electrical way is the best one. So one can do it, and this is a very, I would say, simplified illustration of how one does it, right? So here I have an antiferromagnetic domain. Here is a different antiferromagnetic domain distinguished by the direction of the spins, right? And you have electrons bombarding them and rotating. This is a little bit misleading. This is not really the mechanism, how this is done. This is an inverse spin galvanic effect through spin orbit torque. But the message that I would like to make by this plot is that one can switch antiferromagnetic domains by various means, including electrical way. Recently, a lot of innovative ideas of how one could use antiferromagnets as functional media for novel types of electronic devices came up. This field is called topological antiferromagnetic spintronics. I'm showing just a few examples. One of them here is a topological antiferromagnetic device, actually a transistor, which uses direct quasi-particle current. And the idea there is that the electronic structure of topological antiferromagnet may look like this, with straight line here with no curvature. This is called the Dirac material. And turns out that the band structure, electronic band structure of this material is such that if you switch the direction of the antiferromagnetic moment, the gap opens in the electronic spectrum, and you can build a transistor, a functional electronic element, using this idea. If you combine antiferromagnetic material showing a certain type of quantum Hall effect with an antiferromagnetic superconductor, turns out that theory predicts existence of Majorana fermions at these points, and one can build a quantum computer, at least in theory, using the Majorana qubits. What is more practical, another example that I'm showing here, is a so-called Skyrmion racetrack memory. And the idea here is that you can produce little regions, little circular regions, topological regions that are called skyrmions, in which the direction of the magnetic moment basically is fixed in the middle and get reversed on the boundary. And what I'm showing here is actually the so-called ferromagnetic skyrmion, because you have ferromagnet there and ferromagnet inside, right? But one can also put neighboring spins here, which have a different direction, and then you would get the antiferromagnetic skyrmion. And if one drives the current through such a little wire, a nanoscale size wire, it turns out that there is a drag force which moves those little regions, these little topological regions, antiferromagnetic skyrmions, along the wire, and one can build a memory based on these ideas. One can build a memory built on these ideas, and turns out that the antiferromagnetic skyrmions possess certain advantages, that basically they move faster than the ferromagnetic skyrmions. So multiple ideas of how antiferromagnetic domains can be used in spintronics applications, right? And of course, there is an interesting fundamental science. I will just say a few words about that later. So this is important. Now, antiferromagnets, of course, are already used in the existing magnetic devices, but mostly not as active media, but as a layer pinning ferromagnetism, for example. So this is the actual image of the MRAM, magnetic random access memory device, utilizing an antiferromagnetic element. So those elements are already in use. Let me see. Oh yeah, so I mentioned that antiferromagnets come in a huge number of varieties. Some of them are shown here, meaning that antiferromagnetic order parameter in some cases can be thought as a vector which may have many directions. For example, if another parameter could have 6 different directions in space, then the domain structure of such a system could be topological, could be represented by the so-called Z6 vortices. You see the ellipse here, this is a vortex, this is an anti-vortex, and turns out that those domain structures are topological, and those domain structures, for example, has to do with the theories describing the early evolution of our universe, or if you go to the real theory language, you can consider transitions from the symmetric space to the broken symmetry space through the state of some emergent symmetry, or transition from Higgs phase to Coulomb phase, an equivalent language. And I'm not going into any detail of what I'm talking about here, but the thing is that the physics of phase transition in topological materials could be very interesting as it is, could be related to things that go much beyond the condensed matter physics, could be related to cosmology, could be related to nuclear, to high energy physics and other different effects, right? Now, antiferromagnetic domains are important in everything that I was talking about, but if you want to study them experimentally, you would like to image them. The thing is that antiferromagnetic domains are difficult to image. Now, since antiferromagnets come in a number of different varieties, it's easy to imagine that antiferromagnetic domains also come in a number of different varieties, and let me talk a little bit about the basic types of antiferromagnetic domain varieties. Firstly, you can have the directional domains, which are distinguished by the direction of the magnetic moment in the two adjacent domains. There is a significant number of techniques, experimental techniques, that allow imaging of such domains. They are basically based on the effect that is called magnetic linear dichroism. And there, you basically shine a light with some polarization there So the electric and magnetic field have certain directions. And turns out that, for example, the absorption or scattering of such a light will depend on the relative direction of the electric and magnetic field in the light wave and the direction of the magnetic moment in the material. A well-known example is the so-called X-ray photoemission electron microscopy, or PEM. It uses, as I said, a linear dichroism effect. So linearly polarized light comes, hits the material, kicks out electrons, and the number of such electrons will depend on the polarization of light. So different antiferromagnetic domains will produce, different intensity if you image the electrons that come away from such a sample. I'll skip this one. So Q domains, and these are antiferromagnetic domains distinguished by the wave vector, or the vector characterizing the periodicity of the antiferromagnetic order. They could be directional, but they don't have to be. There are experimental probes that directly couple to Q vectors, such as various X-ray scattering techniques, or actually also it could be electron scattering techniques. And there, basically, you can use a dark field approach to image antiferromagnetic domains with different Q. Basically, you shine your light here, you scatter, you have a signal at some Q, but not other Q, and then you can image antiferromagnetic domains. In this case, these are cycloidal domains in bismuth ferrite. But the most basic type of a domain in an antiferromagnet is of different quality. This is the so-called phase domain. All right. So now I'm showing the example of a phase domain on the simplest possible arrangement, just one-dimensional up-down arrangement, right? So you go up, down, then you switch to down, up, down, up, down, up. In this case, the phase of the order parameter, the phase of the antiferromagnetic order, changes by 180 degrees. This is the so-called anti-phase domain boundary in this case. But in the more complicated arrangements, in antiferromagnets, there could be different phase shift at the domain boundary. But this is the simplest one, the antiphase domain. Now, in some cases, antiphase domains could be imaged by the existing techniques. So, if the symmetry of the material is low enough, this can be done, for example, by the second harmonic generation spectroscopy. And the idea, so these are antiphase domains imaged in chromium oxide using second harmonic generation. But there's the idea is that the symmetry of the material should be low enough in order for the magnetic and the structural signals to interfere in the correct way. In other words, the structural environment of the up spins should be different from the structural environment of the down spins. So very specific symmetry requirements. One can use in principle spin polarized scanning tunneling microscopy, right? So, which in some cases allows imaging spins one by one, all right? Now, this is a very difficult technique to do. It images atoms, it images their spins, and one can image the domain boundary in principle in this case, but as you can imagine, it's very difficult to do and only works very specific, very clean, atomically flat materials in specific conditions. They also must be metals, right? So now, I described some of the existing techniques for imaging antiferromagnetic domains, and recently, well, already not that recently, 2020, we wrote a review on visualization of antiferromagnetic domains. The field is developing very fast, so other important approaches has developed since we published this paper. One of them, for example, is a nitrogen vacancy scanning magnetometry. And there, basically, what you do, you take a piece of diamond and you insert a nitrogen vacancy there, and the nitrogen vacancy carries spin, and you can produce a tip of such a material, which basically carries, one atomically sized magnetic moment. You can scan it along the sample surface, and the method is so sensitive that it can detect stray magnetic fields associated with antiferromagnetic domain boundaries. This is an example of such domain boundaries in some synthetic antiferromagnet. The technique is very sensitive. One example dear to my heart is the material which is called bismuth ferrite, in which you have a cycloid of iron spins propagating in a certain direction, but it turns out that in the direction perpendicular to the cycloidal spin order, there is also a spin density wave. It produces enough magnetic field so that it can be imaged using the nitrogen vacancy scanning magnetometry approach. So this is a useful technique, but as any scanning technique, it is slow and it requires very careful sample preparation. Basically, you need atomically flat surface, or almost like that. Then there are methods based on non-reciprocal NDD, non-reciprocal dichroism. But the idea is that the absorption of light going in one direction material might be different from the absorption of light non-reciprocal directional dichroism. Yes, it's getting late, so it's if you shine light on the material in one direction, the absorption could be different from the case when you shine light on the material from the different direction. Again, it is allowed when certain symmetries are present, and I don't have time to talk about it, but sometimes you can distinguish antiferromagnetic domains when certain symmetry requirements are fulfilled by just simply measuring the absorption of material, right? Okay, but then again, it only happens if a lot of stars come together. Right. So, as I mentioned, phase domains in antiferromagnets are especially difficult to see. So, phase domains then must require a phase-sensitive probe. Ideally, this probe also must couple to the antiferromagnetic order parameter directly, all right? Then you would have a good probe, good experimental approach for doing your measurements. Now, possible approach, as we thought about it, a few years ago, was maybe use magnetic X-ray diffraction. I will talk about it more. Which is directly sensitive to the antiferromagnetic order parameter, to the antiferromagnetic ordering, from a coherent X-ray source, which, ensures that you are sensitive to the phase of the phenomena. Now, the so-called coherent diffractive imaging is already very well known. It comes in a number of different flavors. So basically, you can take your sample, you can shine coherent X-ray in it. Maybe you can even do diffraction using coherent X-rays. Then what happens typically is that, if you have domains in your sample, or if sample has a weird shape, or because of some other reasons, coherent scattering coming from the different parts of the sample will be different. The waves will interfere with each other. They will produce complex interference patterns. Maybe you are familiar with holography. These patterns are related to the holographic images. And if you look at them, they really have nothing to do with, let's say, the domain pattern that is produced inside the nanocrystal. What one can do, one can try to model those patterns and go through complicated iterative techniques and maybe try to reproduce whatever is going inside, right? So this is an example of scattering from a star-like shape, produces something here. Maybe you can recover this shape if you do the correct modeling for this structure, all right? This method is indirect, though all those methods are indirect, in fact. So, and that's a disadvantage, obviously, because we would like to have a technique that is easily interpretable. Also, preferably, we would like to have a technique which, produces large-scale images for a significant area on the sample surface and produces them quickly. Now, I mentioned magnetic X-ray diffraction. I mentioned coherent X-ray sources. It's not so easy to produce coherent X-rays. In the lab, it's probably impossible. But synchrotron sources can do this. This is a photograph of National Synchrotron Light Source 2 at Brookhaven National Laboratory. And sources like that can produce coherent X-rays, in the range of the required energy. And in particular, the instrument that I'm using in this work is the coherent soft X-ray scattering beamline with some parameters shown here. And these are my Brookhaven collaborators in front of an ultra-high vacuum chamber in which scattering of coherent X-rays occurs. All right. Now, I promised to say a few words about magnetic X-ray diffraction, and here they are. This is something that every solid state student is familiar, right? This is the Bragg's law, right? If you shine X-rays at a certain angle on the periodic crystal, you get the Bragg reflection, certain angle, right? Now, people are less familiar with magnetic Bragg scattering, right? But the idea there is exactly the same, right? X-ray scatter of magnetic moment produce Bragg peaks. You can determine the appropriate structure from the position and intensity of the magnetic Bragg peaks. All right, so people are usually unfamiliar. Why would X-rays scatter magnetically? Well, there are two answers to this question. Firstly, of course, X-ray is an electromagnetic wave, right? So there is a magnetic field involved there. But turns out that this magnetic field is not that important for the scattering that I'm going to talk about, right? Okay, so bear with me. The experiment is done as follows. In the standard Bragg geometry, you have incoming X-ray, it scatters from the sample, right? And then you can analyze the polarization of the outgoing light. This is a Pauli Hamiltonian describing the interaction of a light quantum with the electron within the sample, right? And probably with the magnetic field present. One can use quantum mechanics and write down the scattering cross-section up to the second order, as shown here. This is what you get. Now, in this equation, we are neglecting some terms which are small. And then one can characterize scattering in terms of the scattering lengths. Basically, the square root will get you d sigma d omega, the scattering cross-section, which has two terms. One of them depends on the charge distribution within the sample, and this is the standard X-ray scattering that people usually know about, the standard Bragg scattering, which is used for the determination of crystallographic structure. And then the second term, delta F, which is written here, which comes from the second order process here. And in the dipole approximation, and importantly, this is the electric dipole approximation, so this is a strong process. It can be written here, so I replace the current operator with electric dipole operator. Now, the important thing about this term is that it is resonant. Now, what do I mean by resonant? It has a denominator, right? And if this denominator is small, then delta F becomes large, right? So if I tune the energy of the incoming photon in such a way that the denominator becomes small, then scattering becomes large, right? Okay, very well. So the process goes as this. The photon comes, it actually, then there is a virtual process of excitation of some of the electron in this atom to some, energy level, and then it comes back. So the scattering process is completely elastic. You go out at the same energy that you go in, right? So this is a physical picture of the resonance scattering showing here. You are exciting an electron into some higher state, right? And then it goes back. That's a virtual process. Now, too many equations here, right? But I would like to make the following messages. So this term delta F can be decomposed into three contributions. And one of them is non-magnetic because it doesn't contain spin. And then there are two magnetic terms. One of them is proportional to S. The spin, one of them is proportional to S squared. And the important thing is that these terms depend on the polarization vectors E star and E for the incoming and outgoing light, right? So the idea is that if you measure the polarization of the incoming and outgoing light, you can distinguish non-magnetic terms from magnetic terms in this equation, right? So I can ensure that the signal I am looking at is magnetic and it's not coming from the electronic density within the sample. All right. So, two things. Firstly, the signal gets enhanced because of the resonant effect. And secondly, I can ensure that the signal is coming from the magnetic order, not from the electronic order. All right. Yeah, I'll skip that. So, now, the best atoms for making a magnet are here and there, or in the periodic table. Things such as iron, we know, are magnetic, right? So they come with large intrinsic magnetic moments, large spins. I'm interested in the materials containing the so-called 3D elements. And in 3D elements, if you think about it, in the resonance scattering process, your excited electron needs to go to the energy levels that are producing magnetism in order to probe the magnetism, right? This makes sense. You need to put your electron into some magnetic state in order to probe the magnetism. Therefore, you are talking about transitions from 2p to 3d, and these are the magnetic orbitals in 3D elements, and the energies of these transitions are in the region from, let's say, 500 to 1000 electron volts. These are soft X-rays. Right, the so-called soft X-ray energy region. So we must use soft X-rays in order to access the magnetic order in the 3D elements. Unfortunately, soft X-rays get absorbed by air, and therefore you have to do your experiments in ultra-high vacuum. You need to build complicated instruments. Inside this chamber, not only just have the detector, you have the many-circle diffractometer, which moves your sample in space, and other things, right? So those are complicated instruments, but fortunately they exist. Unfortunately, not so many of them exist. Right? But, you know, this is the chamber, specific chamber, experimental chamber that we are using in our measurements. Here comes very simple idea. If you have a sample with two antiferromagnetic domains, which are different by their phase, this is up, down, this is down, up, and you are looking at the magnetic peak, magnetic Bragg peak, right? So incoming beam, outgoing beam detector, you are looking at the image on the detector. The photons scattered from this region of the sample are out of phase from the photons scattered from that region of the sample. So there has to be some destructive interference somewhere in the detector. This is a kind of interference pattern you expect to get, right? Well, okay, if you have many domain walls, maybe you will get something like that. So the idea was this. Take the coherent source of X-rays, shine it on the sample, all right? Coherent X-rays will actually produce diffraction pattern like this on the sample surface. And, you know, if you have just magnetic Bragg scattering, this is what you will see on your detector, right? Once again, this circular pattern is called the Erie pattern, and this is just a diffraction pattern coming from the finite size of the pinhole here. All right. Now, the idea was put domain boundaries there. They will produce destructive interference, right? And you will see the shadows of the domain boundaries on the detector. The one naive way, but not entirely incorrect way of thinking about this is you have a mirror, you plot a dark line on the mirror, you shine light on it, you look at the screen, you will see the image, all right? So, you know, that was the idea. A lot of things need to come together in order for it to work. Our first experiments were done on some particular antiferromagnet, which is rather complicated. We did it because we had this antiferromagnet in our pocket, basically, at the time of the experiment. You know, in science, sometimes the reasons why you do this specific experiment are various. All right? So, this is a uniaxial antiferromagnet, which shows some complicated antiferromagnetic pattern. This is exactly this pattern. The important thing is that you have layers. going perpendicular to the z-axis. Each layer has a net magnetic moment, it turns out, shown by the purple arrow. And the purple arrows, this is antiferromagnets, so they must go up, down, up, down. This would be the antiphase domain. Down, up becomes up, down, right? And we use the specific magnetic Bragg reflection, which was only sensitive to the net moment of the layer. This is 0, 0 L reflection in this case. So this is actually the type of the antiferromagnetic order and the type of the antiferromagnetic domain boundary that we are probing in this experiment. All right. Once again, this is the idea, right? Domain boundary going through the beam, its shadow on the detector. This is what you get actually when you, this is experimental result now, right? This is what you get when you don't have any domain boundary in the beam. So you do observe such a diffraction pattern coming from the circular orifice. This is what you get when you move the domain boundaries in the beam. See those dark wavy lines? This is the unprocessed detector image, which shows the shadows of the interface domain boundary in this specific antiferromagnet that I am showing here. And I can do a lot of sanity checks, such as, for example, this is the magnetic signal coming from the magnetic Bragg reflection. I can take structural reflection and compare these two pictures here, right? I have some structural defects, basically scratches and little things on the surface of the sample, which I can see in both images, but then I have those lines, those dark wavy lines, which I never see in the structural scattering. So this directly confirms that what we see is magnetic signal, all right? So basically what I have here is the image of antiphase antiferromagnetic domains, a specific sample. This is a scale bar on the surface of the sample, all right? Okay, so anyone can already do some interesting science with those samples. For example, you can cool down various times through the Néel temperature. Turns out that the domain boundaries form in different positions, and sometimes they get pinned, actually quite often by the structural defects. This is all quite interesting. I'll skip that. So a few words about the spatial resolution of this method, right? So now, this is a little bit pedagogical, so let me do this. Everyone has seen the single slit diffraction experiment. Actually, the narrower the slits, the broader is the image on the screen, right? So, if I make this beam broad, I expect to see a narrow diffraction pattern on the detector. If this beam is narrow, the diffraction pattern becomes broader, right? So there is like this Goldilocks position right in the middle where I will have the maximum resolution. Turns out that I can calculate exactly the shape of this diffraction pattern. It's shown here. It's in the far field, Fraunhofer diffraction. This situation would correspond to the maximum spatial resolution. I will not resolve magnetic domains smaller than this. And turns out that the pinhole setup resolution, spatial resolution, the minimum size of the domain that you can detect is of the order of the size of the pinhole, but importantly, provided that the pinhole is a certain distance away from the sample. Only then you can get this kind of a spatial resolution. And if you do the calculation, so to achieve the 5 micron resolution, these are pretty large antiferromagnetic domains. You can be a centimeter away from your sample. 1 micron resolution, 0.6 millimeters. You have to put your physical pinhole at such a distance from the sample, which is almost impossible, maybe impossible. If you want to go 100 nanometers, this is completely impossible, right? So, however, it turns out that even for X-rays, we have focusing devices, the so-called Fresnel zone plates, and therefore you can basically move your effective pinhole as close to the sample as you wish by using such an optical element. And that's the next stage. But before I go there, let me just make a little summary of the achievable performance of this method. We can measure our images pretty quickly, limited by the detector speed. 10 to the minus 2 second imaging we have demonstrated, right? We can go a couple of orders better if we use better detectors. We are very sensitive to the magnetic moment. 0.1 MeV we can certainly measure. Spatial resolution of the order of 1 micron with pinholes, but I will tell you that, with the zone plates we can go much better. In a single shot, we can observe a significant area as big as, let's say, 1/2 by 1/2 millimeters. It depends on the pinhole size, penetration, there's many other things, right? And we are sensitive to phase domains of any type. However, provided that the appropriate Bragg reflection is achievable at the surface of the interest, which limits the observable periodicities in the sample, right? Basically to lambda over 2. If the periodicity of the antiferromagnetic structure is smaller than lambda over 2, the wavelengths of the X-ray divided by 2, we cannot see it, and that limits us to things that are, have periodicity which is larger than, 7 to 9 angstroms. All right, now, this is the next example I would like to show. This is another complicated antiferromagnet, uniaxial antiferromagnet. Turns out that if you dope it with if you replace some nickel with manganese, the material has two phases, two magnetic phases. One of them is helical, the other of them was as shown, a collinear phase. I will only be talking about the collinear phase, which occurs below 68 Kelvin. And instead of the pinhole, we'll be using Fresnel zone plate. We'll focus the beam. It turns out that for technical reason, the shape of the beam produced by a Fresnel zone plate is annular. It's not circular. There is like a dark spot in the middle for technical reasons, which I am not going into. But the idea is exactly the same. You put domain boundaries in the beam. You are looking at the magnetic Bragg reflection. You will see the shadows of the domain boundaries in the detector. This is the actual experiment. This is what you see. Okay, so in this specific material, what I'm going to show you, I'm changing the temperature of the sample going from high temperatures to low temperatures. At high temperatures, there is no magnetic order, so I see no image of any type, right? And now, as I'm decreasing the temperature, magnetic signal appears. You start to see the magnetic boundaries, and they evolve. Actually, the domains grow and merge as you cool the sample down. All right? So this is quite interesting. That means that the domain walls are not pinned strongly, and it makes sense for them to grow as the temperature is reduced, because at high temperatures they are produced because of the entropy, right? So yeah, you decrease the temperature, you get larger domains, and this is all very nice. Again, one can probably do some calculations, but this is not the nicest thing that one can do. So let me see the purpose of this. Oh yeah, just to remind you how the method works, right? Now, from the theory of phase transitions, we know that as we go closer to the phase transition temperature, and this is the magnitude of the order parameter for the antiferromagnetic phase, basically this is the intensity of the antiferromagnetic Bragg reflection, right? As we go towards these points, the state should start to fluctuate, all right? So, and in particular, we expect the antiferromagnetic domains not to be static, not to be frozen as they are at low temperatures. We expect that we have enough energy, enough heat energy in the system to make the domains move, all right? Okay, so this is very close to the Néel temperature, maybe half degree or a little bit more than half degree below the antiferromagnetic transition temperature. And this is this is just the video that we take. We can take the images fast enough. This is the real time that you are seeing here. And here you see fluctuations of the antiferromagnetic domains, of the antiphase antiferromagnetic domains on the surface of an antiferromagnet. I believe this is the first observation of these kind of effects in real space, I should say. Yeah. So, sorry. Yeah. One can look at various parts in this image and observe various types of effects. You can observe the directed motion, as I have here, in this part, these are frames from the movies. I start from this, I go through those images here, the bulge kind of develops and moves in a certain direction. So this is just this part from the movie, and I have the bulging protrusion here, right? And if I wait long enough to frame 169, building up suspense. Yeah. Yeah. Nothing happens, right? Oh, no, nothing. No, nothing. Oh, yeah. Wow. Okay, this is the antiferromagnetic domain wall doing its thing, right? Okay, now we can actually describe, do some math and try to find some mathematical description of what's going on in parts of these images. For example, one can ask a question how each of the frames in the movie correlates with each other frame in the movie. In other words, one can calculate the so-called two-time correlation function defined here. I is the intensity. You can do it for a specific area. And for this specific area in the image, you get which looks something like that. And the idea there is that if the area is nice and smooth, then no change is occurring. And once changes start to occur, this is what you see here, right? And from this kind of a picture, you can tell whether things are changing, number one, and number two, how quickly they're changing, and whether, things correlate at this interval of time or different interval of time. If you do this measurement and calculate the two-time correlation function over many, many frames, as shown here, you can make several conclusions, and one of them is that you see, squares of this type, squares of larger type, lines of a smaller size, right? So what this observation is telling us that in the particular fluctuating region of this space, various time scales are present. You go from the lowest time scale that we can resolve, in this particular case it's 0.1 second, to many minutes, all right? So things are fluctuating on different time scale, on various time scales near the phase transition, actually as expected. I have shown you an example of the directed motion, so this bulge and protrusion was moving in one direction, but more typical type of behavior is actually switching behavior, when you have the domain wall going back and forth, as in this image. This is so-called two-state switching behavior, for which one can also make, the corresponding two-time correlation function. You see only the lines of a certain width, in this case indicating that indeed the switching occurs very quickly on the quickest possible time scale. You go back and forth. So Kemp would be familiar with this kind of pictures very well, right? Because this is what you get for the X-ray photon correlation spectroscopy images. Whenever you see something like that, you say there is even evidence for two-state switching behavior, and indeed that's what we get here, all right? So that's a direct confirmation of the theory. And going back to the two magnetic structures observed in the manganese doped nickel telluride, right? So I said that I was so far talking only about this state, which is a collinear state, and in this state only one type of the phase domain boundary is allowed. This is the anti-phase domain boundary. So basically what you do, you switch the direction of all the spins. In a helical structure, however, different types of phase domains are possible. If the structure is commensurate, for example, let's say the period is 3 unit cells, right? In this case, in addition to the 180 degrees phase difference, one can get 120, 60, this kind of degrees, this kind of phase differences between various domains. In this particular sample, though, it would be, well, we had various technical problems studying the helical phase. However, it turns out that if you dope with cobalt, you only get the helical phase. So that samples were easier to look at. And we observed various types of patterns on the surface of the sample. This spotty one actually corresponds to the well-known magnetic bubble domain state. This is the most interesting one. It has stripes, but you see not just stripes, but this kind of funny structures that you have there. This, remember these types of funny structures, because now I'm finally switching to the interesting stuff. All right? Look here, look there. These are the same types of stripy patterns. Right, now, this type of a stripy pattern is topological. It's a dislocation, in fact, right? You cannot remove it by little deformations around the dislocation core. Believe it or not, this is a valid branch of science, the study of topological defects in zebrafish patterns, right? This is the Proceedings of National Academy of Sciences, all right? So this is serious, okay? Now, these are, the same types of patterns that we are observing in antiferromagnetic domain images. So you can get stuffed loops, you can get four-way junctions, you can get three-way junctions. This is a classic dislocation that I have here. All right, so these are all topological defects. Now, I'm showing you the data that we have just obtained very recently. We are still working on it, but this system could. All right, let me just tell you about a couple of observations. We observed that that typically the topological defects are formed in pairs, as shown here. This is what expected for the two-dimensional and three-dimensional system, in fact, with topological defects. But in a two-dimensional system, it turns out that as you heat the system up, a special type of phase transition is observed. And in the cases of melting, it is expected that one gets unbinding of dislocation pairs and the formation of phases which have distinct direction but no periodicity, no spatial periodicity, the so-called hexatic phases, and we have some evidence that we are observing those phases in the melting of the stripy patterns in the antiferromagnet. Now, so this is cool science. Another cool thing that one can do is this. So this is a topological defect here, all right? Dislocation and the dislocation pair. We can get rid of it. How? We just turn the X-ray beam on and off, on and off. In the process, what happens is that you change the local temperature of the sample slightly, by less than 1 degree probably, all right? And then, since what you are doing with the system, you are kind of moving it a little bit in the thermal energy landscape, you are shaking your sample. You are shaking your sample, and then the high energy defect shown here disappears. It gets annealed, all right? It gets annealed. So what it means is that it takes very little of external perturbation in order to modify the antiferromagnetic domain pattern of this material. The domain boundaries are very soft and they can be moved by external probes. Of course, if you go close enough to the transition temperature, this is like 1 degree below the transition temperature, things start fluctuating, and you see this loop, this eye, closing and opening, right? Like blinking, like a blinking eye here. So this topological defect, this loop appears and disappears. These are thermal fluctuations near the transition temperature. At some point, this loop will collapse. It will have enough of thermal shaking. So there is a lot of data for the data analysis, right? And as I said, these are actually unpublished data, so we're still, the loop collapsed, right? Now there is a straight line here, as in zebrafish. So
Question?
yeah.
How thick a region are we looking at?
Yeah, so the experiments done on single crystals, and therefore the thickness of the probed image is determined by the X-ray penetration depth. We are at a magnetic resonance, and therefore this penetration depth is small. It's in this particular geometry, I would say it's of the order of half a micron.
Okay.
This is the thickness of the probed region.
So I should think of this domain is all the way in.
Yes. So the domain boundaries go in. Yes. Right. But then, after 1 micron, they will, maybe they bend, they do their thing. We don't know. We're only probing less than a micron into the sample. Yes, at this particular energy. Let me put it this way.
So you wouldn't expect a KT transition here, right?
Well, the spins are in 2 dimensions. So the question is how they are coupled to each other in the 3rd dimension, strongly or not, right? So since this is a helical arrangement of spins, probably pretty strongly.
So
Yeah.
in the continuous imaging, so there's a photo absorption into the crystal.
Yeah.
So locally heating up, you said by about degree.
I would say smaller than a degree, larger than 0.1 degree. Yeah.
So
like
then the
that.
cooling, I assume, is through the phonon to the crystal, to the rest
No,
crystal.
you just absorb light, and that leads to heating. I mean,
Yeah, I understand. But if this thing is totally isolated, then the temperature will keep on rising.
Sure.
If you right.
Yeah, sure. Yeah.
And
There is some thermal current, going into the sample. There is it's sitting on a cold finger, so there is some type of thermal equilibrium in the end, right?
Okay.
Yeah. All right. So, let me conclude then, right? So, I tried to say that antiferromagnetic domain imaging is important. May find, antiferromagnetic domains may find applications in future information technologies, but such imaging is difficult. I presented, a new domain boundary imaging technique which is applicable to many antiferromagnetic domain types, but importantly to the phase domain type, including antiphase domains. The technique produces direct images. You don't need to do any kind of artificial image reconstruction. Works in situ and in real time. I expect in the future, we're working on it to get interesting and important results for physics of phase transitions, studying phase transitions in antiferromagnet. We have already observed thermal fluctuations of antiferromagnetic domains in real space for the first time. The technique allows in-situ domain control, and therefore it will be applicable to device-like structure. For example, you may want to study Hall-type effects, and Hall-type effects in topological antiferromagnets may depend on the presence of antiferromagnetic domains within your device, right? So we should be able to see these domains or characterize their size and what they do, right? Some of those results are published in this paper, some of them are unpublished, but of course the most important result is that we can get movies, and movies are cool. Thank you very much.
Question?
I was just curious. So how possible is it to confirm whether the crystalline defect is sort of possible? Is the reason why the topological defect, the dislocation that you're seeing, are sort of?
Whether the dislocation is somehow pinned by a crystallographic defect?
Right. Yeah. Because I think till now, we only have probably in photonics that we've seen that these dislocations they do come due to like dislocations.
Firstly, the length scales that we are probing here are micron size, right? So they have nothing to do with atomic structure, right? There could be some local structural imperfections that pin the domains, right? Yeah. In those particular cases that I were showing you, we couldn't see anything on in the sample topography, but such defects could be there, right? What we didn't check is whether the topological defects always form in the same positions in the sample. Now, we believe they're not, actually, because what we see, the main structure is very soft, right? So we can modify it by little thermal gradients. We can anneal the topological defects, right? So they're certainly not strongly pinned to whatever can pin them in the sample. Yeah. Of course, structural defects may play their role in this case. In the case of the first images that I was showing, non-fluctuating domains, in the first sample, we saw some evidence of the magnetic domain boundaries pinned by structural defects, which we actually physically see on the surface. Yeah, so that is also possible.
I hope you don't take my comment that I'm about to give in a negative way.
No.
I don't believe this is a thermal fluctuating domain walls. I think what it is you have a heat source heating the sample, and with this complicated heat flow, so the temperature gradient in the sample is all over the place. So what you are seeing here is
I cool a couple of degrees below. The pattern is completely flat.
No, that's fine.
But the gradient is actually becoming bigger. The gradient and the heat flow, right?
Okay, so if it's equilibrium, let's do you can just look at the time dependence, and then you can
Yeah, you can observe this for hours, right?
No, I understand that. You can do it, then you could partition a principle, and you estimate some of the energy scales.
Another argument. Whenever we have a heat flow, it should produce some evidence for the directional motion, right?
You do?
And in most parts of the sample,
Yeah.
it's a switching behavior, back and forth, back and forth, back and forth. So you see, overall, the majority of those fluctuations are not directional. Right? So, two arguments. Number one, you can freeze this behavior very easily by changing temperature. Number two, we don't see evidence for the directionality of the effect, and the heat flow is directional.
What I suspect is if you thin this crystal down, make it very thin, and put a gold finger in the back to heat sink this very probably, all of this will go away.
Yeah, would be a very interesting experiment to do. Moreover, heat gradients may play their role, right? But I gave you a couple of arguments that these are more related to thermal fluctuation. Experimentally, yes, one can try to do what you said.
Then, if it's really a thermal fluctuation of the domain walls, then you can do a standard fluctuation dissipation analysis to see plot some numbers. So, for example, the domain wall energy, right?
Very good idea. Yes. Yeah.
And did you do it?
No, because
If it is, this would be the first thing to do, right?
How?
Well, you do your image and measure the position as a function of time, plot it and then bin it, and then
that's a
do
lot
this.
of work. This is in our plan.
So you get
we
like
haven't
a
done it
diffusion
yet.
constant out of it, basically, like a.
You get it. So basically, you get a dissipation coefficient as well as a
Diffusion is a
and then some kind of a modulus.
Diffusion is a directional effect. You must have something moving in a certain direction. Gradient of something and motion in this direction, right?
I think this. My criticism can be addressed directly by just thinning the sample down and then remeasure, see if there's a difference.
Yeah.
I think then you immediately will shut me down.
Absolutely.
Right? Then I'll be very excited and say, hey, let's do it.
We haven't done such experiment. Maybe possible to do, right? I gave a couple of arguments why we believe in the thermal, right? Heat gradients may have their contributions.
The reason I don't think it is because I expect something to do a lot faster than this. If it's true, thermal fluctuation, because
near, this one can always argue that this is far enough from the near transition, so things are slow, right? You can go closer, and then probably there are fluctuations which we are not seeing, right? Yeah. In fact, as we get closer to the near transition, the domains will become very small. They will become nanoscale. Instead of this image, you will see the speckle pattern. We see it, right?
Across transition, I would expect that the same
At the
critical
transition,
opalescence, right?
Well, I mean, from nanoscale size domains, you get the speckle pattern.
Okay.
Well, it is fluctuating, right?
Right.
But we cannot measure fluctuations that are faster than 0.01 second, whatever, right? Yeah. So this is what we measure. Maybe there is a lot of faster fluctuations very close to the near temperature cannot tell.
Can you chop it?
Chop what?
The beam.
Well, have you tried this at a free electron laser? Can you? So you can do a stroboscopic type measurement. Your detectors can't go much faster, but you could do maybe some of these chirping measurements and things like this.
Yeah, you probably can. Yeah,
Yeah.
that's right. Yeah. With 3 beamlines in the world, maybe we'll
If they give you some
in the next 100 years, right?
There's only a couple beamlines in the world where you can do this as well, right? So
Right, but it has, it's more, I have access there. I can do more than one experiment in 5 years on this beamline.
yeah. Have you been able to analyze more detail any scaling in the physical size of the domains with temperature?
I would love to. Not yet. Firstly, I'm not sure if I have enough information in the image of this size, right, to do any kind of scaling. Always involves power loss, right? I may not have enough space here.
And I guess you have to estimate something about the size of the domains inside the sample, because you might be.
Sample, I don't have
know,
any
right?
information, right? For the inside. If I see the.
It could be anywhere within the absorption.
Right. Yes. Exactly. Yeah. Right. Yeah. So I would like to do some kind of a scaling analysis, but one needs to invest a lot of time into this.
Right.
This is one of the things that is on our list. Yeah. To try to get spatial correlations, because time correlations, you can get from XPCS, for example, right?
Mm-hmm.
But here the difference is that we get the real space patterns, so we see spatial correlations, right? And we can try to characterize them. Yeah. But it's not like something that you can do in a week. You need to determine ways of, you have whatever, 10,000 images here. For each image, you need to, to get the line, right, the domain boundary, determine the size of the domain, do things. For example, we see correlation between the curvature of the domain boundary and its fluctuations, right? So high curvature supposed to be high energy domain line, and we typically see that the high curvature regions move easier, right? So this is consistent, yeah. And flat regions, they move, but not as vigorously. Yeah.
Mm-hmm.
A lot of things to analyze here. A lot of information in those images, but maybe not enough for establishing the scaling laws.
Okay. Oh well, maybe we can come up and talk, because we're 10 minutes over already. Yeah.
Hope it was.
Let's get a quick.
Yeah.
I got this impression that the z direction was like very important, and the antiferromagnet coupling was the domain wall essentially was created because of there's antiferromagnetic coupling here in the z direction, and then you have the plane here, and then the domain wall is like this. So I was wondering whether if this technique can also be used for two-dimensional materials. Because here
In a two-dimensional material, we don't have enough volume to produce scattering signal. If you are talking about a few monolayers of stuff,
Okay,
Then not. If we have, I don't know, several hundreds of nanometers of stuff, sure, we have enough signal, right? But we cannot study a monolayer or two.
Is the antiferromagnetic coupling important for if we are talking about a few?
Yeah, yeah, sure.
For example, like the twisted bilayer graphene and that sort of stuff.
Twisted bilayer graphene, again, it's not enough material, at least for us, to get the signal.
I see. I see.
From a few monolayers. Not saying it's impossible, and somebody mentioned the free electron laser. That's enough intensity there. Yeah. So in principle.
Right.
Yeah.
Yeah.
It is a very good question about thermal gradient. We spent some time thinking about it.
Yeah.
Whether it's really purely thermal fluctuations or thermal gradients have contribution.
Yeah.
Yeah.
Yeah. Yeah, I mean, if you can make a micron scale sample, then that starts to address. I don't think it fully addresses it.
No, but
You know what
we tried actually very recently. We tried a very simple experiment. We have a local heater on the sample.
Yeah.
We
And
send,
watch it. Actually, just see if you can drive it.
We send, yes.
Yeah.
No, really. So we
Yeah.
send the pulse of current. We heat up locally.
Yeah.
And we haven't really seen the directional motion so far.
The heating is different though too, right? The way you're heating the sample with a resonant X-ray beam, you're putting the heat right into the electrons.
Correct.
That are into the magnetism. With the heater,
No, in the end, once you get the thermal equilibrium, it's like
that's right. Yeah,
It's
it
a
quickly equilibrates,
heating.
but it's a different coupling process to begin with. But I wonder, yeah. You could also we had this conversation about beam heating. If you can really do this equipartition argument, you could maybe, this is a technical thing and maybe not as interesting for general audience, but you can actually say something really specific about local thermal gradients from beam heating.
very difficult.
Yeah, perhaps.
Yeah,
But it seems like you know there's information. It's a very information-rich measurement.
Information rich, right? But we are struggling with
Was maybe
finding
too rich.
resources
Yeah.
for
Yeah,
the
yeah.
right analysis.
Yeah, that's right.
Because the tools are not available, right? The tools are
Yeah.
not available. We have to create them.
Yeah.
But that requires effort.
Yeah. All right.
Thank you for the great talk. I think this is the first time I've seen the topological dislocation in actual materials. Like, I think whatever I've seen is they're only in photonics that these measurements are.
Yeah, or
Which is
or
really
films
exciting.
and things like this. Yeah.
Yeah. Thank you.
But probably in ferromagnetic fields, they probably exist. Yeah. I'm not claiming anything about magnetism in
So you have
general.
that,
Just antiferromagnetic.
That pointer.
Oh, it's
Let's grab that.
yeah. Don't.
All right. That's great. I have a question for you too. Actually, it's one of our projects. Maybe we can ask you quickly, and then we can call a lift.
Right.
When's your train actually?
I'll show you the